Hi, today we're going to talk about polyprotic acids. And so polyprotic acid is one that has more than one proton that it can donate. And one of our most famous is phosphoric acid. It's probably the most famous of the weak acids. And what I want to show you is that it's going to lose an H+. The first one's going to make dihydrogen phosphate ion. And we can write the Ka expression, and I'm hoping that now you're a lot more comfortable with the Ka expressions. And here's the Ka1, 7.2 times 10 to the negative 3. And let's go ahead and practice how to write the pKa, just as review. And I believe it comes to 2.14. Just as a reminder how important pKa's are. Now, the thing about dihydrogen phosphate ion, which is this one, is that it is a conjugate base of the weak acid, but it still has acidic properties. So it's both acid and base. And it's going to lose its second proton to form monohydrogen phosphate and H3O+. And we could get the pKa value for that. I believe it's 7.20. Let me just double check that. So we're going to take the negative log of 6.3 times 10 to the negative 8. Okay. And then monohydrogen phosphate will ionize again to form phosphate ion. And if let's write the pKa from that Ka. And I'm plugging that into my calculator. So that's 12.38. Okay, so a couple of really important, super important ideas. First of all, know how to write these ionization equations. The tendency is going to be that you're just reading them and not writing them. That will not help you at all in further chemistry. So know how to write these equations out. Secondly, let's take a look at the trend in Ka values. Started off small, but then it got smaller and then super small. So this is always going to be a trend with our weak polyprotic acids, that we have a very small Ka. So this is for sure a weak acid. But then it gets weaker until we get to the weakest. So with a number like 10 to the negative 13 here, that means that the equilibrium for that one lies very far to the left. And then this is also small, the 10 to the negative 8 value, so that one lies left. And what that means is that the pH is going to depend only on the first ionization. These ones here will be negligible in terms of pH. Okay, let's go to the next slide. Here's Ka1s for these weak acids. Notice the trend. The first Ka is always larger than the second. And then the second is always larger than the third, and thirds tend to be very, very small Ka values. Now, if we talk about how this will affect pH, let's take a look at ascorbic acid. Now, ascorbic acid has a scary formula, but in this case, we have it here as a simplification, H2ASC. So let's go ahead and write with me on your paper. The first ionization. And then we could also talk about a second ionization, but let's take a look at the values. So here's Ka1, a weak acid, kind of typical Ka value, but look at Ka2 is ridiculously small. So the only one that's going to determine the pH is this first one. And then it's just a regular weak acid problem. And hopefully you guys are getting better at those, because those tend to, at some point, seem easy. Okay, we'll run through our approximate to make sure we can not use quadratics or assumption. And for sure, that's going to be greater than 400. So we'll be able to ignore that x. Okay, and they'll work this out for us in just a second, but I just want you to make sure that you understand that polyprotic acids tend to be just weak acids as any other because they're Ka2s, or Ka3s, if applicable, are negligible because they're so small. So let's take a look. That's what this next slide is saying. So we'll go to the actual calculation. So here's our Ka1. Like we said, we can ignore that x. Oops. We can ignore the x. And that's going to be shown on the next slide. Up here, this x value is very small. The assumption is true. And so we can solve for the H3O plus concentration and then plug that into the negative log to find our pH. Okay. The second dissociation or ionization will not contribute to this. Okay,